Okay, I think I got it. We can start now. Good morning, everyone. Thank you all for being here. Today we have the pleasure of hosting Dr. Gaetano, and he'll be talking about particle mixing, vacuum structure, and all of that. Doctor, thank you very much for accepting the invitation, and you may start whenever you're ready.
Okay, let me try to share my screen.
Okay.
Okay. Okay, so can you see my screen?
Yes, you can see it.
Okay. Okay, so thank you to the organizer for inviting me to this very interesting series of seminar. This is my first year I know about this series, but as I was talking with the organizer, this is not the first edition. So congratulations also for organizing this very interesting event. And I slightly changed the title of my talk, but more or less the content is the same. And well, the topic of my talk maybe is a little bit different from the topic of previous talks because it's more theoretical, but I hope it's still interesting for you and for the audience. And well, let me say that it is more closely related to the topic of Professor Matzas, the previous talk by Professor Matzas about Young effect. And I kindly invite you to recover that talk if you missed it, because it's very, very nice and very pedagogical about the importance of the Young effect for the quantum field theory. And I say that it's closely related to that topic because I show you how to use the Young effect for testing properties of some fundamental particles of the standard model, which are indeed neutrinos. Okay, so, well, these are some references if you are interested in more details. Of course, I try to be not too much technical, to not bother you, but I mean, if you are interested, maybe we can discuss later, or you can find details in these works. Okay, so, well, let me start by trying to frame my analysis. So let's try to understand motivation for this specific study. Well, we know that neutrinos are, in some sense, magic particles because they can change their flavor during the space-time evolution, during the space-time propagation. You can imagine, you can think of the flavor as a sort of internal quantum number of neutrinos, which characterize the identity of these particles. The first approach to the theoretical study of neutrino mixing and the consequent phenomenon of neutrino oscillation was done by Pontecorvo in his work in 1978. In particular, Pontecorvo assumed that the states of neutrinos, the eigenstates of the evolution, the eigenstates of the Hamiltonian, here we are working in a simplified two-flavor approximation, but you can repeat the same consideration also for three-flavor neutrinos, which is maybe the most realistic scenario. So, well, to describe this change of identity, this change of flavor during the space-time propagation, Pontecorvo assumed that the eigenstates of the Hamiltonian, which are these μ1 and μ2, they do not coincide with the eigenstates of the flavor operator, which are these μe and μ, but they are rotated, okay, according to this very simple transformation where this theta is the mixing level. Okay, so you can easily understand that if the eigenstates of the Hamiltonian does not coincide with the eigenstates of the flavor charge, so these two operators, they do not commute, so they do not have common eigenstates. So during the space-time propagation, the flavor is not conserved. And this phenomenon of change of flavor is usually referred to as flavor oscillation. Okay, these considerations, they work in quantum mechanics because here we are considering the single particle states, so we are in quantum mechanics, but in quantum mechanics, of course, you can understand that the phenomenon is very easy to explain in some sense, because here we have just a rotation between these two bases, between these two representations, rotation, as well known as unitary transformation, because they satisfy this property. And if we have two bases, two representations that are connected by a unitary transformation, they are physically equivalent, because I mean, we can simply describe the physics both in the one basis or in the other one. These two bases are connected by a unitary transformation. So in terms of probability, we know that the physics is more or less the same. So there is no, let me say, conceptual issue in this quantum mechanical treatment. Okay, as I was saying, maybe we can imagine, this is, well, we can imagine the flavor of particles as...
Sorry, but may I ask a question?
Yeah, sure.
It's just, I mean, I never studied deeply neutrino oscillation, so maybe it's a stupid question, but initially we thought that neutrino were particles without mass, massless particles. But now we know that they have some mass, but even though they are relativistic particles. So why can I use the usual quantum mechanics to describe the evolution of these states?
No, okay. Well, first, this is the first treatment by Pontecorvo. Okay, so this is not maybe the most rigorous treatment, but this is the first treatment by Pontecorvo. You can describe, you can simply use, I mean, I don't understand, you mean the evolution?
Yeah, the evolution of these states. I mean, why do they respect Schrödinger's equation? The usual quantum mechanics.
No, okay.
They respect something like Dirac equation.
No, okay, so these properties, they are true for these massive states, Nu1 and Nu2. For Ni and in mu, the situation is a little bit more complicated, and we are going to see what happens in the maybe some of the next slides. But in principle, these particles, Nu1 and Nu2, they are the particle with definite mass. So in principle, they are the particles which respect all the standard laws of quantum mechanics.
Okay.
Thank you for the question. Okay, so I was saying we can imagine this flavor as a sort of color, but color, I mean, should not be interpreted in the sense of color of quarks. You have to, I'm just trying to make an intuitive representation of this phenomenon of flavor oscillations. You can think of the color as you can interpret the word color in this context in the everyday meaning of the word. So you can say that the neutrinos, they change their color during the evolution, during the propagation, and you can interact, you can see this change of colors because you can detect the flavor of neutrinos. Okay, just to stress the importance of this phenomenon, quite recently in 2015, Professor Kajita and Professor McDonald, they were awarded with the Nobel Prize for the discovery of neutrino oscillations. In particular, Kajita was responsible for the Super Kamiokande experiment in Japan about oscillation of atmospheric neutrinos, while McDonald was responsible of SNO experiment, Solar Neutrino Observatory experiment in Canada. And they were awarded with the Nobel Prize for the discovery of neutrino oscillation, which imply, as Lucas were saying before, which implies that neutrino have a mass. And I show you in a while why the phenomenon of neutrino oscillation, the fact that we observe neutrino oscillation implies necessarily that at least one generation of neutrino should be massive. Okay, so as I was saying, this is the standard the original quantum mechanical picture where we work with single particle states, but we know that the quantum field theory, which is maybe the best quantum theory we have so far, it is based on fields. The fundamental object is not the single particle states, but are the fields. So a field theoretical analysis of mixing is all the more needed. Okay, one of the approach to the field theoretical study of neutrino mixing was made in this work by Blasone and Vitiello in 1995. The question they ask is, what happens if we try to implement the mixing transformation I was showing you in my first slide, but at level of fields, not at level of single particle states. So now these objects are fields, not single particle state anymore. So this is the standard Pontecorvo transformation. And again, we try to implement this rotation, this mixing transformation at level of fields. So these are the standard massive fields, which, are here. I'm working in the Dirac, I'm supposing that neutrinos are Dirac particles, but we don't know. This is an open problem. I'm going to tell about this problem in a few moments. But let's suppose for a while that neutrinos are Dirac particles. So let's quantize the neutrino fields in the standard Dirac-like way. So these are Dirac spinor. And this is the standard, the standard quantization of a Dirac fields. So this is for the massive fields. But now the question is what happens for the flavor fields? So if we introduce this quantization in this equation, we can see that the flavor fields, they acquire this specific form where all the information about the mixing is now contained in this new ladder operator, which I'm calling alpha chi and beta chi, where chi can be E or mu. Okay, how is defined this new ladder operator? Is defined in this way. So you can see that at level of fields, and in particular at level of ladder operator, we don't have just the Pontecorvo rotation, simply the Pontecorvo rotation, but we have the combination of the Pontecorvo rotation and also a Bogoliubov transformation, which is absent in quantum mechanics. The coefficients of this Bogoliubov transformation, they are defined in this way. They are products of these Dirac spinors. You can see that, okay, while this first term arises from the product of Dirac spinors for particles with different masses, U2 and U1, this extra term is related to the product of a spinor for particle and spinor for antiparticle, okay? So, well, this is a very important point, very crucial point. Again, in quantum field theory, we have at level of ladder operator, we have the Pontecorvo rotation and also a Bogoliubov transformation. This Bogoliubov transformation, which maybe you know from superconductivity or from the Hawking-Ringo effect, this Bogoliubov transformation is highly non-trivial because it's responsible for the inequivalence, unital inequivalence between the Fock space built on the flavor vacuum and the Fock space built on the mass vacuum. So while in quantum mechanics, I was saying that the flavor and mass bases, they are unitarily equivalent because they are connected by a simple rotation. Here, this inequivalence is no longer anymore because of the appearance of this Bogoliubov transformation. Indeed, if you try to compute the scalar product of the flavor vacuum, which is this guy here, by the mass vacuum, when I say flavor vacuum, I mean the vacuum annulated by this operator, this flavor operator, while this vacuum is the vacuum annulated by this operator alpha 1, alpha 2, and beta 1, beta 2. If you try to compute scalar product of these two states in the infinite volume limit, in the quantum field theory limit, you can see that this product is 0, which means that the two states are orthogonal, which means that the two Fock spaces built on these two states, on these two atla, they are inequivalent, okay? So in other terms, we can say that the flavor fields and the mass fields, they live in different Fock spaces. Okay, here I just present you, but I'm going to be very briefly, this is just the structure of this flavor vacuum, which is a generalized coherent state, Perelomov-like coherent state. It's a generalized because, as you can see, it is populated by particle-antiparticle pairs with different masses and also opposite momenta. So we have this couple, one couple, this couple here, this couple here, this couple here. But this is a generalized state because we also have objects with 4 units here we have a particle, antiparticle with mass 1 and 2, but we have also a particle with mass 2 and antiparticle with mass 1. So this is, I mean, again, we have a couple of particle, antiparticle, but also objects made of 4 units. So in this sense, this is a generalized parallel-like coherent state. We can also compute the density of mass particle in the flavor vacuum. This calculation is quite straightforward. And if we compute this condensation density, we can see that this is non-zero, this is non-vanishing, but it's proportional to the sine squared of the mixing angle, and also this Bogoliubov coefficients, which I propose you again, is given by this expression. You can simply see that if we work in the approximation where there is no mixing, if M1 is equal to M2, it's quite easy to show that this coefficient is 0, because in that case, we are just multiplying the Dirac-Spinor with mass, let's say 2, by the Dirac anti-spinor with the same mass, because in the case of no mixing, 2 and 1, they are the same index. Okay, so in that case, this coefficient is 0. So the condensation density goes to 0. So we don't have anymore any inequivalence between the two representations if we are in the absence of mixing. And the same happens if we put theta equals 0, because in that case, again, we don't have mixing. So in the limit where there is no mixing, we recover the standard we recover the standard quantization for definite mass fields. Okay, let me just spend a few words on the mathematical details of this inequivalence between flavor and massive Fock spaces. We know that in quantum mechanics, there is this very beautiful theorem, the Stone-von-Neumann theorem, which guarantees that for systems with a finite number of degrees of freedom, which are quantum mechanical systems, all the representation of the canonical commutation relation, they are unitarily equivalent. So they are physically equivalent. You can think, for instance, to the Schrödinger and Heisenberg representation of quantum mechanics. We know that they are equivalent. We can work either in Schrödinger or in the Heisenberg picture, but there is no substantial physical difference. But what happens in quantum field theory? In quantum field theory, again, we have fields. Fields have infinite degrees of freedom, objects with infinite degrees of freedom. So this theorem does not apply anymore, does not hold anymore. And indeed, in this case, in quantum field theory, we have many unitarily inequivalent representation of the canonical commutation relation, which means many vacuum, which means many different Fock spaces. In the specific case, I'm talking of this inequivalence between flavor and mass, but you can think, for instance, of theories with spontaneous symmetry breaking, where the same set of equation or dynamical equation, they both describe the unbroken and broken symmetry phases. You can think of the Hawking-Wundt effect, where we have the full quantization for the Minkowski observer and the full quantization for the Rindler observer in the case of the Wundt effect, or the full quantization for the static observer outside a black hole, and the full quantization for the free-falling observer. These inequivalents between such quantization are possible only in rigorously studied only in quantum field theory, because again, in quantum mechanics, this theorem guarantees that all the representation of the canonical commutation relation, they are equivalent to each other. Okay, so we can think the quantum field theory has a sort of book, and each page of this book is a different quantum mechanics. And when I say different, I mean a unitarily inequivalent quantum mechanics. And you put together all these quantum mechanics and you have the quantum field theory. Okay, now the specific question for my study is, okay, we know that in quantum field theory, the flavor and mass representation, they are not equivalent anymore. So the question is, which is the fundamental representation for neutrinos, or in general for mixed particles? The flavor or the mass representation? And when I say fundamental, I mean, which are the states to be used? here for the computation, for instance, of the scattering matrix, for the computation of the probability amplitude in the process we want to study. Flavor or mass? So that's the main question, or the main issue, the main question I'm going to study. Okay, just to try to convince you that this is not only mathematics, this is not only theory, I show you this plot of the intensity of the tritium beta decay versus the kinetic energy of the emitted electron. And okay, you can neglect this blue curve because this is for massless neutrinos, but we know that neutrinos are massive because of the flavor oscillation. So you can see that there is the difference between the green curve, which is for flavor eigenstates, and the orange curve, which is for mass eigenstates. The difference is very, very, very small, but it's non-vanishing. Of course, such a difference is currently below the sensitivity of current experiments. So for the moment, we don't have any experimental evidence to say that neutrinos, fundamental neutrinos, must be massive or flavor neutrinos. But this is to try to convince you that the problem is here. The problem, is not just a theoretical problem, it's not just a mathematical problem. This difference, we know that the quantum mechanics is in some sense the non-relativistic approximation of quantum field theory. So the difference is more rigorous the difference between the quantum mechanic and quantum field theory approach is more evident in the non-relativistic limit. We know that neutrinos are highly relativistic, so for the moment we don't know how to treat. It's not easy to address this dichotomy from the experimental point of view, but maybe there is some hope with non-relativistic neutrinos from the cosmic neutrino background. And recent experiments, such as Ptolemai and so on, they are going to study this cosmic neutrino background. So maybe there is some hope to see this difference between the flavor and mass states for the spectrum of these specific neutrinos. But again, for the moment, we don't have any experimental support. One more evidence is given by the oscillation probability. This is the quantum mechanical formula, the standard Ponte Corvo formula. And here you can understand why the observation of flavor oscillation necessarily implies that neutrinos, at least one generation of neutrino, should be massive, because this delta omega is essentially proportional to delta n, the difference between two generations of mass. So if this probability is non-vanishing, and we know that is non-vanishing because of the experiment awarded with the Nobel Prize, this delta omega must be non-vanishing, which means that, again, at least one generation of neutrinos, at least one n in this difference, must be non-vanishing. So this implies that neutrinos should be massive. Okay, so I was saying this is the standard quantum mechanical formula, but if you try to compute the oscillation probability in quantum field theory, well, first, how do you define the oscillation probability in quantum field theory? In quantum mechanics, you simply compute this amplitude, okay? You simply compute the bracket of the state. For instance, this is the probability that an electron neutrino generated maybe at time 0 is detected at time t as a muon neutrino. This is simply the bracket mu tau, mu t, mu e. And this is the result you obtain in that context. But if you work in quantum field theory, where we don't have single particle states, how to define this oscillation probability? Well, you have to construct a flavor charge operator, which is defined as follows. This is the charge operator for the flavor key. Key again can be mu on mu. If we compute, this is the definition of the charge operator for the fields in chi. If you compute the expectation value of this operator, the normal ordered operator on the state, for instance, mu e, if you put e as an index here, you are computing the probability that at time t, your states e is still detected as an electron neutrino. instead, if you put here mu, you are computing the probability that after a time t, your initial state E is detected as a muon neutrino. So to compute the oscillation probability, we simply put Q mu here. So it means that here we have to consider mu. And if we compute this oscillation probability, you can see that the resulting formula is this one. So this neglect for a while these Bogoliubov coefficients and neglect for a while this extra contribution. This is exactly the term we have in the quantum mechanical limit. But now, because of the Bogoliubov transformation, we also have these additional terms, this Bogoliubov coefficient here, and this Bogoliubov coefficient here, which multiplies sine squared of 2 theta and sine squared of a term which is proportional to the mass, to the sum of the frequencies, or if you want, the sum of the masses of the two particles. So while the standard term is proportional to the difference, this extra contribution, which is an exquisitely theoretical contribution, is proportional to the sum of the mass. But in principle, this should not be surprising, because if you try to study two coupled mechanical oscillators, if you try to solve the dynamical equation, you can see that you have two contributions. One proportional to the difference of the masses of the oscillator, and the other one which is proportional to the sum of the masses. So in principle, this extra contribution should not be surprising at all. Now, you may wonder how this formula reduces to the Pontecorvo formula, because we know that Pontecorvo formula is covered. As far as we work in a specific regime, which is the regime of highly relativistic neutrinos, we know that this formula works well. So we need a limit where this equation should reduce to the Pontecorvo formula. This is a necessary condition to say that this equation is not sufficient, but a necessary condition. Which is this limit? Again, is the relativistic limit, as I was saying before. Because if we consider K, the momentum K much higher than this scale, which is given by the two masses of the massive fields, M1 and M2, one can show that this coefficient goes to unity, this coefficient lambda goes to 0, so this contribution disappears. This is 1, and we exactly recover the standard Pontecorvo formula. So we can simply say that the Pontecorvo formula, the quantum mechanical Pontecorvo formula, is the relativistic limit of the full theoretical formula. Okay, here just a plot to see the difference between the full theoretical and quantum mechanical formulas. You can see, if you consider K much smaller than the product of the two masses, the difference is evident. On the other hand, if you work in the relativistic limit, K much higher than the square root of the product of the two masses, you can see that the two curves exactly coincide with each other. And this is what I was saying before. In the relativistic limit, this quantum field theory approach reduces to the quantum mechanical approach. Okay, here just a list of some other open problems about neutrino physics, but I'm not going to discuss all these problems. First, we don't know the exact value of neutrino masses. We don't know the hierarchy. I mean, if the difference between M1 and M2 is higher or smaller than the difference between M2 and M3. We don't know, as I was saying in the beginning, if neutrinos are Dirac or Majorana particles. The only proof, the only test, okay, to establish whether neutrinos may be of Majorana type is the neutrinoless double beta decay. But so far we don't have any experimental evidence of this decay, so we cannot say nothing. Again, sterile neutrinos, if there are extra neutrinos which do not interact. If there is CP violation, which is predicted by the standard model, but for the moment we don't have experimental signature. And then there are also problems more related to cosmological aspects. For instance, if neutrinos, some species of neutrinos can be candidate of dark energy, dark matter, and so on. Okay, Well, this is the first tool. Now let me very rapid also on the other tools, which is fundamental for my study, the Unruh effect. This was, as I was saying, this was explained by Professor Matsas in his previous talk. The Unruh effect, you know better than me. It's just a prediction of quantum field theory, which states that from the point of view of a uniformly accelerated observer, the inertial vacuum, the vacuum for inertial observer, for Minkowski observer, is not vacuum, but is perceived as a thermal bath of particles with a T, with a temperature proportional to the acceleration. And this was predicted by Hamro in 1976. Also in this case, we have some experimental problems, because if you put here numerical values, you can see that in order to detect a temperature of 1 Kelvin, you need an acceleration of more or less 10 to 20 meter over second squared, which is a very huge acceleration. So far, we don't have any direct evidence of this Unruh radiation, but Unruh and also other groups, also from Brazil, they are working on possible and direct evidences of Unruh radiation. Okay, this is just a simple way to derive this Unruh effect. You can introduce these Ringler coordinates. Let's suppose for a while that the acceleration is along the x1 axis. You can introduce these new coordinates, which are related to the Minkowski coordinates by this transformation. You can write the metric, the Minkowski metric, in terms of these new coordinates. I mean, it's just a matter of simple calculation. You can show that this trajectory, this branch of hyperbola, is the trajectory for a uniformly accelerated observer in the relativistic medium. So a uniformly accelerated, or more simply Ringler observer, will move along this trajectory. When I say Ringler observer, I mean uniformly accelerated observer in the relativistic medium. You can easily understand that such an observer, which is confined along this hyperbola, is causally separated from the region R minus, because this line acts as a future event horizon. Because if you construct the light cone for each event of the space-time, you can see that the observer in this region cannot receive any signal from the future F, from this part of Minkowski space-time, and cannot send any signal toward this past region. So this line here acts as a future event horizon. This line here acts as a past event horizon. If you combine these two observations, you see that 1 and 2 regions, they are causally separated, causally disconnected. Okay, and this is fundamental for the emergence of the Unruh effect. Okay, again, just a pictorial representation. You can see this is the accelerated observer who feels this thermal bath in the vacuum for the Minkowski static observer. Okay, Unruh effect, as I was saying, I mean, for the moment, we don't have any direct experimental signature, but the Unruh effect is a solid prediction of quantum field theory, because you can derive this effect from different independent perspective. The Bogolyubov transformation approach, which is the original approach used by Hamru, but there are also many other approaches. For instance, you can use the Unruh-DeWitt detector approach. You can also involve this time-dependent Doppler effect. This is a pedagogical work by Alsing et al. So this is just to try to convince you that although we don't have experimental evidence, the Unruh effect is a fundamental ingredient of quantum field theory. Okay, now, well, after this maybe quite long introduction, let me come to the main point of my study. Again, do not forget that the main point of my study is trying to understand which is the physical, the fundamental representation for neutrinos, flavor or states. I made this digression about the Unruh effect because the Unruh effect is fundamental to in my study, is fundamental to establish, to try to explore more in depth this dichotomy. Okay, so let me talk about the inverse beta decay. We know that, well, thanks to this work by Mueller, we know that the decay properties of particles, they are not universal. for instance, the most emblematic case is the case of the proton. We know that in the standard model, protons are stable particles. As far as we consider the standard model, so we are not considering more exotic theories, just the standard model. We know that the proton is stable because the observed lifetime of the proton is higher than 10 to 10 years, so which means it's higher than the current age of the universe, which means that so far we have to consider the proton as a stable particle. How this observation is explained in the standard model, because the standard model requires the conservation of the baryon number and also the energy conservation. If you simply rely on the baryon number conservation, in principle, the proton may decay into a neutron. But this process actually, as far as you consider static proton, okay, this process is not allowed because we know that the proton is less massive than the neutron, so this process is violated by the energy conservation. In general, the proton cannot decay at all because it is the lightest baryon. So if you combine these two requirements, you deduce that in the standard model, the proton cannot decay. Static proton, okay? But what happens if we let me say kick the proton, if we accelerate the proton, if we give enough energy to the proton to overcome the difference, the mass difference between proton and neutron? Well, in principle, this process is not forbidden anymore, and this is usually called the inverse beta decay. The proton can decay into a neutron, a positron, and an electron neutrino. Okay, so let me emphasize this point. If you are considering static proton, the particle is stable in the standard model. But if you try to accelerate the proton, and if you give to the proton enough acceleration, enough energy, the process is not forbidden anymore. So in principle, it could decay. Okay, this is just the same process I was commenting a few seconds ago. Okay, well.
Just a silly question, please.
Yeah.
You're saying that accelerated proton can decay into a neutron, a positron, plus a neutrino.
This is two level.
But the proton is a charged particle. Why don't you have electromagnetic waves there, a photon?
No, but this is, I mean, this is just the simplest process you can have at level. Okay, it's just the inverse. No, in principle, you may.
Electromagnetic wave should be emitted.
Yes, but in principle, but you mean because of the acceleration or in general?
Yeah, because of the acceleration of a charged particle.
Ah, okay. You know, yeah, oops, sorry. Yes. In principle, you can. I mean, you can also consider photon, but this is again the simplest process you can obtain. Okay. I mean, for the conservation of baryon number and energy conservation, this is enough.
Okay.
So this is the simplest process. Maybe you can make this process more complicated. You can go also, you can also consider loop. So you can also consider photon emission of some other particles. But in principle, at 3 level, this is the simplest and so the most likely process you can obtain. Okay, so well, this is a, let's say, schematic representation. Your proton, which is decaying into a neutron, a positron, and an electron neutrino. But now the question is, okay, this is the process in the lab frame, in the laboratory frame, where the particle is accelerating. Okay, but now the question is, what happens in the co-moving frame, in the frame co-accelerating with the proton, where the particle is at rest? So in principle, there should be no decay. But that's not the case. The process, thanks to the Euro effect, occurs also in the co-moving frame, because let's say that in some sense the proton has memory of its acceleration, because it interacts with a thermal bath of electrons and neutrinos due to the Hulu effect. So at 3 level, we have these 3 processes, which are the counterpart of this process here, but in the co-moving frame. So for instance, the proton can pick up an electron from the thermal bath, thermal bath, and decay into a neutron and an electron neutrino, or can pick up, for instance, an antineutrino and decay into a neutron and a positron, or can pick up both an electron and an antineutrino and decay into a neutron. And this occurs thanks to the Unruh effect. Well, a systematic approach to the study of the inverse beta decay was made by Van Zelle and Matsas in this seminal work of 1999. There are some approximation, but in principle, they are reasonable approximation. Well, they used massless neutrinos, so no mixing, because I mean, if there is no mass, of course, there is no mixing. They work in the non-recoil approximation, which means that it's possible to consider your system proton-neutron as moving along the uniformly accelerated hyperbola without any deviation from such an hyperbola. And then also this extra condition on the acceleration, which allows to use the Fermi-like effective theory. So here we are describing the interaction by means of the coupling interaction scheme. This is the nucleon current. We are describing the neutron and proton as a two-level system. Okay, sort of proton is the unexcited state and neutron is the excited state of this two-level quantum system. This is the nucleon current. This is the monopole operator. This is the forward velocity of your nucleon system. And this delta just fix the trajectory of the nucleon along the hyperbola. This is the lepton current, which is in state quantized. So this is a semi-classical approximation. And this is quantized. So this is the neutrino field, sorry, and this is the electron field. Okay, in this approximation, one can try to make computation. This is the transition amplitude for the inverse beta decay in the laboratory frame. This is the transition rate. Okay, you can just compute this quantity, which is a scalar quantity. One can show that, okay, it's not evidently a scalar quantity, but one can show that this is a scalar. This is the probability over the nucleon proper time. And this is the result you get in the laboratory frame. Okay, this is a Bessel function. I don't want to stress too much on technical details, just you should know that computation are possible in this approximation. Now, what happens in the commuting frame? You have to consider those three processes we were commenting above. If you compute the transition amplitude for these two processes, and then you compute the whole transition probability, you get this expression. If you work a little bit, if you manipulate a little bit this expression, you can see that the two decay rates, they are exactly equal to each other. So this is fundamental for the covariance of quantum field theory because you are considering a scalar quantity. So since we are simply moving from the inertial observer to the Rindler observer, and this can be done by means of coordinate transformation, in principle, we expect that a scalar quantity should remain the same, should be unaffected. And this is possible thanks to the Unruh effect, because if you not consider the Unruh effect, you don't have these three processes. So in the laboratory frame, you have a decay rate which is non-vanishing, while in the commuting frame, you have zero. So in that case, you will have a violation of the covariance of quantum field theory. Okay, here there is a plot of the proton lifetime versus the acceleration, and as you can see, for very large acceleration, the proton lifetime takes finite values, while for vanishing acceleration, the proton lifetime goes to infinite, which means stability of the particle, as we will do. Okay, so far, this consideration again were developed using the approximation of massless neutrinos, but now we said, okay, we know that neutrinos are massive. What happens if we include also the mass of neutrinos? Okay, the first work on this topic was made by Aluali, Alabun, and Torrieri in this quite recent work. The author claimed that while in the laboratory frame, these sentences are taken from their paper. They claim that if in the laboratory frame, the interaction is the standard electroweak interaction, so in the lab frame, the fundamental neutrinos should be the flavor eigenstates. On the other hand, in the commuting frame, they claim that the proton interacts with neutrinos in Rindler states. These states have an effective thermal weight, so they must be considered as massive eigenstates. If flavor eigenstates were used also in the commuting frame, then the thermality of the Unruh effect would be violated. So in order to preserve the thermality of the Unruh effect, the authors work with flavor eigenstates in the laboratory frame, with massive eigenstates in the cumulative frame, and they conclude that the two decay rates disagree when taking into account neutrino mixing. But for the comments I was saying above, of course, this implies a violation of the covariance of quantum field theory, because we are saying that a scalar quantity is not the same in the two frame, which is quite absurd. So, I mean, we cannot accept such a result, violation of covariance of quantum field theory. So, well, in some sense, we can say that the general covariance is a sort of lighthouse for our study. We start from the preservation. We want to preserve the general covariance of quantum field theory, and then we see what happens to the other ingredients. But a fundamental point is the general covariance of quantum field theory. To be physical, a theory, of course, cannot be representation dependent, cannot be coordinate dependent. Okay, so general covariance is fundamental. So let's say that we are the paladins of general covariance. This is more to present, in some sense, my collaborator. This is Professor Massimo Blasone from University of Salerno, Professor Gaetano Lambiase from University of Salerno, and this is Luciano Petruzziello, which is currently a postdoc here in Salerno, but now is spending some, visiting in Germany at Ulm University. Well, the point we are not too much convinced about the claims of the paper by Aluvalia and collaborator is this central point. Because it's quite easy to see that if you work in the Pontecorvo approximation, so if you use, this Pontecorvo approximation, if you use this equation at level of ladder operator, remember, in the Pontecorvo approximation, you don't have the Bogoliubov transformation I was showing in one of my first slides. In the Pontecorvo approximation, your ladder operator is just cosine theta alpha 1 plus sine theta. This is unity. This is 0 alpha 2. So it's just a rotation of alpha 1 and alpha 2 in the Pontecorvo approximation. So in this case, it's easy to show that if you compute the density of flavored neutrinos in the Minkowski vacuum in the Pontecorvo approximation, since the ladder operator are simple rotation of nu1 and nu2, you directly obtain cosine squared times the distribution of nu1 particles plus sine squared times the distribution of nu2 particles. But consider now that this omega, which is the Ringler frequency, this is the standard Planckian spectrum, the standard Fermi-Dirac distribution. Consider that this spectrum here, the frequency which appears in the Unruh spectrum, does not depend on the mass of your object. So in principle, this guy here is equal to this guy here. So you can factorize this thermal distribution. This is unity, and you recover the standard Unruh distribution for E. So as far as you work with Pontecorvo states, which is the limit where they are working, you don't have any violation of the thermality of the Unruh effect. So in principle, this claim has no computational support. It's just a claim. So, we preserve the thermality of the Unruh effect, and we can say that Unruh is happy as far as we work in this limit. But some deviation from thermality occurs if you work in the full theoretical approximation, because now you have two Bogoliubov transformation, one related to the Unruh effect, the thermal Bogoliubov transformation responsible for the Unruh effect, and also the Bogoliubov transformation responsible for mixing. You can show that these two transformations, they combine in a non-trivial way. So if you now try to compute the spectrum of mixed particles for the Ringler observer in the Minkowski vacuum, this is given by the sum of the standard thermal factor plus non-thermal correction. You cannot rearrange this result in a Planckian-like form. So you cannot define a T, you cannot consider this as a Planckian thermal spectrum. But again, this occurs in quantum field theory, not if you work with Pontecorvo states. So this is not the case we are considering, that Aluvalia and collaborator are considering. And so, well, Huru in this case may be a little bit disappointed because the Huru effect is no longer thermal, but I mean, this is just a result of theoretical computation. Just an heuristic interpretation of this deviation from thermality, you can see that if you do not consider mixing, what happens? In that case, you just have this first and second configuration. Okay, you have, in the standard case, so with no mixing, you have that new radiation is generated by only one type of antiparticles falling into the event horizon. So you have just one type of particles, which you can see, which enter, which make up the Unru thermal radiation. But what happens if you also include mixing? Well, in that case, you can see that you have, I mean, a blue particle, let's say a blue particle may correspond to a blue antiparticle fallen into the horizon, but also to a red antiparticle fallen back into the horizon. So this corresponds to an increase in the entropy of your system, and so a modification of the Planckian spectrum. So this is an heuristic way, let's say, simple way to understand why we have a deviation of thermality in the presence of mixing, and also a deformation of the statistics. Well, in a recent paper, we show that this departure from the standard Boltzmann-Gibbs statistics can be interpreted in terms of Sully's language. Very, very briefly, Sully's statistics holds true for complex systems, for system where there are long range interaction or long time memory, or strongly entangled system. And since the flavor vacuum is made up of entangled particle-antiparticle pairs, in principle, these Sully's statistics, this Sully's distribution, which is defined by this equation, can be a good paradigm to describe the new statistics in the presence of mixing. Well, consider that this Q is not the base of the logarithm, it's just a definition. Log Q of zeta is defined in this way. So this is, of course, if you apply the maximum entropy principle from this modified entropy, you can derive the modified Planckian distribution, which is, okay, bosonic or fermionic, according to the system you are describing. If you try to expand these statistics for small q, q is the parameter which quantifies departure from Boltzmann-Gibbs statistics. Since this departure, if they exist, they should be very, very small. Of course, you expect that this q equal 1 is the standard Boltzmann limit. And since, as I was saying, these deviations are very small, we expect that q is very close to unity. So in principle, one can expand this modified distribution for small deviation of q from unity. And this is the leading order of the Sully's distribution. On the other hand, this is the leading order of the non-thermal distribution we were obtaining here, just more explicit computation. And you can see that you can identify, at least the leading order, these two deformed spectra, provided that q minus 1 takes this value. Of course, for delta m equals 0 or theta equals 0, this is 0, so q is equal 1, so we recover the standard thermal spectrum. But in principle, let me summarize. So if we work with Pontecorvo states, which is the assumption they are using in this work, and also the assumption we shall use in our work, you have no violation of the thermality of the Unru effect. This occurs if you consider also this extra Bogoliubov transformation, which is not the case we are considering. So this is just a derivation. So this is what I was saying before. This claim, as far as you work in the Pontecorvo approximation, is not supported by computation. So in principle, it's wrong. And indeed, let's see what happens if we consider flavor eigenstates as fundamental states, both in the laboratory frame and in the commodity frame. This is the computation in the laboratory frame. Now we have the sum of three contributions. This contribution is related to mu1. This contribution here is related to mu2. And this contribution of diagonal contribution arises from the interference of mu1 and mu2. These terms are defined in these two equations. So this is the computation in the laboratory frame. In the co-moving frame, well, computation are maybe a little bit more technical, more complicated, but you can do as well computation also in the co-moving frame. You get this very awkward expression. Let's compare now these two results. Let's see what happens. Okay, these are the two results, laboratory and co-moving frame, using flavor states as fundamental, both in laboratory and co-moving frame. One can see that this guy here is equal to this guy here. This guy here is equal to this guy here. So the question is, what happens to these two terms? Are they equal or not? If they are equal, okay, we can say that the two decay rates, they are equal to each other. So with flavor states, we preserve the general covariance of quantum field theory. If not, there is some residual problem. Okay, so the problem again is about these two of diagonal contribution, these two interference terms. Are they equal or not? Well, computation are non-trivial, maybe you can see from this picture, but if we work in this approximation, which is heuristic approximation, because we know that the mass difference of neutrinos are very, very small, you can see that also these off-diagonal terms are equal, at least to the leading order. So we have equality between the two decay rates using flavor states both in the laboratory and co-moving frame. So flavor states are consistent, they preserve the general covariance of quantum field theory. And this is a way to infer properties of fundamental particles of the standard model using a fundamental principle of quantum field theory. But quite surprisingly, and I'm almost close to the end, quite surprisingly, just one day after we put on the archive our paper with flavor eigenstates as fundamental states, just one day later, it was published this other paper on exactly the same topic, the study of the asymptotic nature of neutrinos with the inverse beta decay. But the claim in this paper is that the fundamental states are the massive states rather than the flavor states. So they use massive states both in the laboratory frame and in the co-moving frame. But let me try to convince you why this setting, the usage of massive states as asymptotic states, may be a little bit problematic. Well, first, it's not true that, because the author says that flavor states can be defined only phenomenologically, so a physical Fock space for flavor neutrinos cannot be constructed. Well, first, this is not true, because in this paper, there is a quite rigorous construction of flavor Fock spaces for neutrinos, which has some issues, some problems, but in principle, we have a construction of the Fock space for flavor neutrinos. Then you can see that if you use the massive states, the massive neutrino here, you can see that you have a violation of the flavor charge, because here you have a proton, so zero flavor charge in the initial states. Here you have an anti-lepton of flavor alpha, but if here you put the massive neutrinos, of course, this implies a violation of the flavor charge, because this has flavor charge, let's say -1, but this doesn't have any flavor charge, because this is a massive state. So this implies a violation of flavor charge, which is not allowed in the standard model at level. Flavor charge is conserved in the standard model at level. Then you can see that if you work with asymptotic massive neutrinos, you have just one term in the decay rates. If you remember, with flavor neutrinos, we have this three contribution, 1, 2, and 3, and this last one is related to the interference between μ1 and μ2. If you work just with μ1 or μ2, you don't have any interference, and this interference is responsible for neutrino oscillation. So it's quite tough to describe oscillation in this way, but more important, it's quite tough, as I'll show you in a while, to describe CP violation in neutrino oscillation with this massive picture. Okay, so these are the processes in the laboratory frame if we include also oscillation. This is the process we were considering before, neglecting oscillation. This is the process if we consider also oscillation. This is the standard symbol to indicate flavor oscillation. You can compute the decay amplitude for such a process, then you sum this to decay amplitude, and you get such a straightforward result, such a simple result in the laboratory frame, including oscillation, using the flavor states. This is the corresponding computation in the moving frame, in the co-accelerated frame. These are the three processes I was mentioning before, and these are the corresponding processes if you include oscillation. Again, we make this sum, we compute the total decay rate, and you can see that again, using flavor states, there is agreement between moving and laboratory decay rates. So flavor states are consistent with the description of flavor oscillation, but let's see also whether these states are consistent also with CP violation. CP violation, as I was mentioning in the beginning, they are predicted by the standard model, not yet observed, but they are a fundamental ingredient of the standard model. So if we accept the standard model, CP violation is there. In order to have CP violation, we have to generalize all the consideration made so far to free neutrino generation, because it's necessary to have one phase in this phase is the CP violating phase, and this is non-vanishing only if you consider at least three generation, because if you consider two generation, you can always put to zero this extra phase. So we need at least three generation of neutrinos. So we generalize all the consideration to free generation, and of course we expect that physics does not depend on the parameterization of this matrix. And the only invariant quantity which we can construct from this matrix is the so-called Yalskov invariant, which is defined as follows. So in principle, we expect if we want a result which does not depend on the parameterization of the Pontecorvo, Maki, Nakagawa, Sakata matrix, all the results, observable results, they must be proportional to this J, which I stress is the only invariant measure of CP violation we can construct from this matrix. Let's see what happens using massive states and flavor states. With massive states, you compute the decay rate for the process, for the inverse beta decay. Then you compute the corresponding amplitude for the CP violating process. You compute such a difference, and you can see that such a difference is zero, because if you are using massive states, here you have the same matrix element. Here there is the matrix element. Here there is the conjugate of this matrix element, but here appears a modulus squared. So in principle, this difference gives zero. So if you don't have the possibility to predict CP violation using massive states as asymptotic states for neutrinos. On the other hand, if you use flavor states, you can see that you compute again such a difference, and you can see that such a difference is proportional to J, to the Yalskov invariant, which is what we were expecting because of the consideration we were making before. So we can say that flavor states also pass this Porter test. They are consistent with the general covariance of quantum field theory, but also okay, this is just a summary of the three approaches. The approach based on flavor and massive states, it's not consistent with the general covariance of quantum field theory. So we are quite confident that such an approach is not, is not correct because violates the fundamental covariance of quantum field theory. So the decision is between mass or flavor as a asymptotic representation for neutrinos. The mass approach is consistent with the general covariance of quantum field theory. You have seen that, but it violates the lepton charge conservation in the vertex. It's not clear how to describe CP violation in neutrino oscillation. On the other hand, the usage of flavor states seems to be consistent with all these requirements. So in principle, our point of view is that the flavor asymptotic representation is the fundamental representation for neutrinos, but not only neutrinos, for all the mixed particles. Okay, just some final slides, just to show you that such a result, is also supported by other papers in literature. For instance, here, this is a recent review by Bilenki, which is one of the main collaborators of Pontecorvo, who put in this process the flavored neutrinos. Are the flavored neutrinos which participate in interaction. So the flavored neutrinos are the only neutrinos that we can detect, not massive neutrinos, but flavored neutrinos. Also, in this other paper, it is mentioned that the physical states are the flavor states. In this more experimental paper, the author claimed that neutrino oscillation are a quantum mechanical phenomenon where neutrinos are created in flavor states and observed in flavor states. So these are the states. When I say fundamental, I mean the states, the physical states, the states that interact, the states that we can produce and detect. Also in this further paper, okay, just to mention some recent paper in literature. So this is the main claim, the main results of our study, that the physical representation of neutrino states in presence of mixing are the flavor states. Thank you.
Thank you for a great talk. I have a couple of questions. Okay, first, does anyone have any questions? If not, then I'll begin myself. Okay, go ahead.
Yeah, I have several actually, but you can talk first.
Okay, thank you. All right. First thing is, your claim is flavor states are necessary for the description, but I think there's a quite recent paper from Matzes. I think it's titled "Neutrino Mixing Without Flavor States." I think I haven't read it with very detail, but I think he considers the dynamics of the emission and detection of neutrinos also. But your claim is mostly that when using mass states, we have lepton number violation and the problem with the CP violation. I mean, that's the main argument, let's say.
Mm-hmm.
But the neutrino oscillation can be recovered by using only mass states.
Yes, okay. In that paper, they claim that it's possible to recover neutrino oscillation also using massive states. But one of the points I don't share of that paper is that they use this phenomenological definition of the. They claim that the flavor states can only be defined phenomenologically in the sense that the flavor states depends, the definition of the flavor states depend on the specific process you are considering. Okay, so this is one of the main arguments in that paper. And so they use the massive states. They say that the neutrino states is in some sense related to the process you are considering, but this is quite hard because we need a definition which is in some sense universal. Okay, cannot depend on the specific process. And in that paper, if I well remember, they study their picture is somehow detector dependent, which is, from my point of view, is not, a fundamental picture, cannot be a fundamental picture, because if you say that the description of a particle or a state of a particle depends on the process, you are just making an effective description, not a fundamental description, because in principle, you first should know the process, all the properties of the process, all the features of the process, and then you can put the state of your particle. But more general, we need a, let's say, universal theory. The more the theory is universal, the more is fundamental. You don't have this problem with flavor states. You don't need any detector, knowledge. You don't need any knowledge about the detector. You can define this these flavor states, or is this full theoretical flavor states, or is this full theoretical flavor states. Okay, simply this is the vacuum, but you can obtain the single particle states, letting this ladder operator acting on the vacuum. So these states can be, it has some problems, some issues, but you can define regardless of the specific process. So in my point of view, this is more fundamental than a definition which involves the specificities of the detection process. And then the other point, sorry, in that paper, if I well remember, they only consider two generation and they do not consider the problem of CP violation.
Oh, yeah.
Could you confirm this? Because I read some time ago.
Don't remember
I'm
that
quite
some
sure.
time ago, but
Okay,
I
but
think
I'm
it's only
quite
two
sure.
flavors. I think it's only two flavors, yeah.
I'm quite sure they do not consider CP violation.
Yeah.
Even if you can describe neutrino oscillation using these detection-dependent assumptions, then I don't understand how to describe CP violation, because you have this problem here. If you try to compute such a difference, you can see that here appears the same guy, basically, so this difference is 0. So you don't have any possibility to describe CP violation. Again, let me say that we don't have so far any empirical evidence of CP violation, but CP violation, they are predicted by the standard model. So in principle, if we accept that standard model is the best theory we have so far, in principle, we should be able to describe also these ingredients, which can be described if you use flavor states.
I have another question. It's concerning, like, in the beginning of your talk, where you're talking only about the neutrino oscillations. The full quantum field theory computation of the probability have some correction terms.
In here, right?
Exactly. Have these corrections terms.
Yeah, these red highlighted terms.
Yes. With current technology, are these measurable?
No.
Okay, so
these are below the current sensitivity. But maybe let me stress this point. The main difference between the full theoretical approach and the quantum mechanical approach is expected to arise in the non-relativistic framework for non-relativistic neutrinos. Because if you consider this relativistic limit, you see that this rho is 1, this lambda is 0, so you recover the standard Pontecorvo formula, okay?
The relativistic limit.
In this relativistic limit here, okay. These extra correction, they are more prominent for non-relativistic neutrinos. Okay.
That's a little bit odd. I mean, I have a computation with full quantum field theory, and when neutrinos are
okay.
Considering the relativistic limit, we have standard quantum mechanics with the same prediction. Is that right?
Sorry, maybe I didn't understand your question. Please, can you repeat?
So, okay, you have the full probability with the quantum field theory computation.
Okay, this one.
And in the relativistic limit, you recovered the same thing you compute using standard quantum mechanics, which is non-relativistic. I mean,
okay. No, let's. I mean, non-relativistic in the sense that you can see this limit. I mean, you recover the standard formula in the limit where quantum field theory reduces to Pontecorvo approximation.
Okay.
So far, we only can detect neutrinos, or we can mostly detect neutrinos which are highly relativistic. So this means that these corrections are very, very, very small and below the sensitivity of current experiments. Non-relativistic neutrinos are neutrinos from the cosmic neutrino background. And some experiments in recent years, some experiments are trying to explore that field. So maybe there is some possibility to detect signatures of this correction from data related to these experiments. But so far, we don't have any experimental possibility to distinguish, okay, between this formula here and this formula here.
For the current experiment, Pontecorvo formula is enough for now. For experiments.
Yeah.
Okay.
Which is the reason why we are trying to find a solution theoretically. Okay, waiting for experimentalists, answer or insights. We are trying to approach the problem theoretically.
Great, thank you. Lucas, if you have any question.
Yeah, I do have. First of all, many thanks for the amazing talk. I think I started understanding the problem. Thank you very much.
Maybe I'm sorry because I'm now realizing that I put too much arguments, too much consideration. Maybe the point. I don't know if you took my point, if you caught my point.
Yeah, no, that's okay. I think I started understanding. I took note of some references that I will read now and try to understand more of this thing. But just a question. You are talking about thermality of Unruh effect of neutrino fields and things like this. It's just a general question. How do you prove thermality? I mean, do you compute something like KMS condition or?
Yeah, the KMS. Indeed, the authors in this paper, they explicitly refer to the KMS condition.
Okay.
Yeah, I didn't mention here, but thank you for.
Okay. No. Then it's okay. Then it's a standard way to just the thermality is. And do you know if there is something related to fluctuation relations in these things? I mean, fluctuation theorems. Because you KMS condition studying transition probabilities and things like this. So do you know if there is someone studied some sort of fluctuation dissipation theorem for these kind of fields?
But you mean related to deviation from thermality or?
Yeah, exactly like that.
No, I remember there was a paper, but honestly, I don't remember the others where they were trying to, because as I was saying, we don't have experimental signature of the Unruh effect, but if I well remember, there was a paper I read many years ago where they were trying to study, at least to explore signature of Unruh effect studying at fluctuation of the vacuum rather than the distribution, which is maybe more easier to detect. I don't know, I'm not too much expert, but I remember there was a paper where they were looking at fluctuation rather than, I don't know if this is related somehow to your question or not.
Oh yeah. I'm interested in if someone.
I have to recover that paper because I just read some years ago. It was very nice because it was one of the first attempts to explore the Unruh effect, looking not at the distribution, the vacuum distribution, but fluctuation and correlation in vacuum distribution. But I have to recover that paper.
Oh, if you can remember, I'll have to read this thing.
But if I will remember, it was related not to deviation from thermality, standard Unruh effect.
Okay.
Thank you.
I mean, one more general question. You talk about the Unruh effect and related effects. Do you know if there is some sort of Casimir effect for neutrino fields?
For neutrinos, okay, for photons, sure.
Yeah.
For neutrinos, I don't remember actually.
Because there are for photons, there are for gravitons. Actually, to gravity, they also have at least one paper that does this. But for neutrino fields, I never thought about.
No, indeed. I'm thinking, but no, maybe it exists, but I don't. No, I never read any paper on Casimir effect with neutrino physics. But in principle, we have to see if it is experimentally accessible. I mean, a Casimir effect with neutrinos, but
will not be for sure. I mean, I have
but you know,
the fact that exists, this will not be feasible from the experimental side. This for sure.
mm-hmm. No, but theoretically, no, I don't remember any paper. But I don't want to say. I mean, I want to check better. But at the moment, I don't remember any paper studying this topic.
But I mean, in principle, it's possible because we need to change the boundary conditions of the field. We know that for some fields we cannot do this because we need too much energy, especially if you want to change it, the boundary conditions dynamically.
No, there is. Okay, no, there is a paper. Now I remember. Maybe. Okay, no, there is a paper, but were not for neutrinos, but for mixed boson fields, if I will remember. Because it was just to, I mean, to simplify computation because you don't have any structure, and so it was just a toy model. Okay, let's say like this. And yes, there is a paper, and now I remember I'm also one of the authors of this paper. And okay, we studied, but it was a toy model. Okay, many years ago we studied this toy model for the Casimir effect, and what you see is that okay, there is a difference in that case if you consider flavor fields or massive fields, but again it was much below the sensitivity.
Okay.
Mm-hmm.
Okay.
Thank you.
Okay. Many thanks again for the talk. Unfortunately,
thank you for inviting me.
I have to fill up some issues here, bureaucratic issues, and it was really a nice talk. Many thanks.
Thank you. No, it would be nice if we can keep in touch to discuss
this for
better
sure.
some other points. Many thanks. Thank you.
Okay, so thank you for accepting the invitation for the amazing talk. Surely I want to do a little bit of research on that, and so I'll probably be in touch.
Sure. Thank you for inviting me, and let's keep in touch.
Yeah, thank you.
See you. Bye-bye.
Goodbye, everyone. Bye.